So I want you to picture this. You are standing right in the middle of Times Square.
Oh, yeah. Absolute chaos on a good day.
Right, complete chaos. But it is 5 p.m. on a Friday, and the sky is just completely opened up, and it is pouring rain.
There's literally the worst possible time to be stuck out there.
Exactly. I mean, you've got sirens blaring, there are thousands of tourists shoulder to shoulder, and the yellow cabs are just completely locked in gridlock.
Nobody is moving.
Right. And you're getting soaked to the bone. So what do? You pull out your phone, you open an app, and you hit request ride.
Like we all do, yeah.
Now, count to 3. 1, 2, 3. Your phone buzzes. A car has been matched to you, and it's suddenly appearing on your map, navigating that exact chaos, and it is scheduled to arrive in exactly 3 minutes.
And, we take that entirely for granted.
We really do.
But the reality is, when you tap that button, you aren't just, like, sending a digital text message to a driver.
Yeah.
You are triggering what is arguably one of the most complex, high-throughput, real-time spatial routing engines ever built by human beings.
And that is exactly what we are getting into today. Welcome to the deep dive. Today, we are pulling apart the blueprints of that exact system to figure out how it actually works under the hood.
It's a fascinating architecture.
It really is. We're looking at a highly technical, production-grade breakdown of Uber's core system architecture. And if you're listening to this right now and thinking, well, I'm not a software engineer, this sounds incredibly dense.
Please do not worry.
Yeah, don't panic.
Yeah.
We're going to translate all of this system design jargon into pure, fascinating aha moments.
Because, to make that car appear on your screen in 3 seconds, the system literally has to pull off a mathematical and engineering miracle.
It does. So let's just set the baseline here, because the scale we are dealing with is, well, it's almost hard to comprehend.
It's massive.
Yeah. According to our source material, we are talking about 1 million active drivers online globally at any given moment.
Right. And then you have to combine that with 50 million daily active riders who are opening the app, dragging the map around, and requesting rides.
Just a massive amount of traffic.
But, the number that really defines this entire architecture is the telemetry.
The GPS data.
Exactly. Those 1 million active drivers are sending a continuous stream of GPS location updates.
Like constantly pinging the server.
Yes. We are looking at a sustained load of 250,000 to 500,000 individual GPS pings hitting the system servers every single second.
See, that is the number that just completely broke my brain. 500,000 times a second.
Yeah, 500,000 times a second, a car somewhere on Earth is telling the server, I am here, now I am here, now I am here.
And here is the physical limit, like the ultimate constraint placed on this entire system.
Yeah.
When you tap request in the rain in Times Square, the system has to filter through all of that global noise.
I love it.
It has to find your exact location, scan all the nearby drivers, score them based on a bunch of complex behavioral factors, and lock down the absolute best match.
And it has to do all of that in under 100 milliseconds.
Under a tenth of a second. I mean, it is quite literally the blink of an eye.
It has to be. Because, if it takes longer than that, the user experience degrades.
Right, you get the little spinning wheel of death.
Exactly. If the system stutters, you see that wheel, you get frustrated, maybe you close the app, or, and this is worse, the driver you were supposed to get actually moves out of the area while the computer is trying to do the math.
So they're just gone. So the fundamental question here is, how on earth does a computer actually map the Earth to track 1 million moving cars that quickly?
It's a huge problem.
And reading through the source material, I was really surprised to find that the very first problem they had to solve wasn't about servers or data cables. It was actually about geometry.
Yeah. The map itself is broken.
Right. Or rather, the way we have historically thought about digital maps is broken. Because for a long time, spatial mapping just relied on squares.
Yeah, that's been the standard for decades. Traditional systems like Google's S2 geometry or geohashes, they basically take the globe and lay a massive grid of squares over it.
Like a giant piece of graph paper.
Exactly. Think of graph paper just wrapped around the planet. And, it seems entirely logical at first glance.
I mean, sure, human beings build cities and grids. Our screens are made of square pixels, so why wouldn't we map the physical world in grids?
But the architecture documents completely reject this. They state that the square grid has a fatal geometric flaw.
Yeah, and I was trying to visualize this while reading, and I keep coming back to a chessboard.
That's a great way to look at it.
Right, so if I have a piece on a chessboard, and I move it 1 square forward, just straight ahead, orthogonally, that is a set distance.
Yeah.
But if I move it diagonally, I am physically traveling a further distance to get to the center of that next square.
And that right there is the core of the problem.
Just that little bit of extra distance.
Yeah. If we go back to high school geometry, the Pythagorean theorem dictates that the diagonal of a square is the square root of 2.
Okay.
So it's roughly 1.4 times longer than the side of the square itself.
Right.
So in a digital mapping system that's built on a grid of squares, your diagonal neighbors are mathematically 41% further away from the center than your orthogonal neighbors.
Okay, I understand the math there, but I have to play devil's advocate for a second. Why does that tiny geometric quirk actually matter?
I mean, it sounds pedantic, right?
Yeah. We are talking about cars driving on real, messy, winding city streets. Who cares if the computer theoretically thinks a car is 41% further away in one very specific diagonal direction?
Well, it wouldn't matter if we were only tracking one car.
Yeah.
Remember our scale, 500,000 updates a second. If a backend system is using squares, every single time it wants to calculate the distance between a rider and a driver, or even just figure out which drivers are clustered in a neighboring square, it has to constantly run complex trigonometric edge corrections.
Wait, so it has to do trigonometry for every single movement?
Yes. It has to compute sines, cosines, floating point math. It has to account for that 41% variance depending on the specific angle of approach.
That sounds exhausting for a computer.
It is. Computing heavy trigonometry 500,000 times a second is an incredibly fast way to just melt your servers.
Wow.
Because, computer processors, CPUs, they are very good at simple integer math, like adding 1 plus 1.
Right, basic arithmetic.
Exactly. But floating point arithmetic, dealing with decimals and complex geometry, that requires entirely different, much heavier processing cycles.
So the CPU overhead just gets catastrophic.
Yeah, you simply cannot scale a real-time proximity engine to a global level if the fundamental geometry of your map requires constant mathematical corrections just to figure out who is standing next to who.
So the shape itself is literally creating a massive computing bottleneck.
Exactly.
To fix this, the source details how Uber developed and open sourced this radical solution called H3, which is a hexagonal hierarchical spatial indexing system.
It's quite a mouthful.
It is a very fancy way of saying they threw away the squares and they brought in the hexagons.
Yes. They project the Earth's 2D spherical surface onto an icosahedron.
Oh.
An icosahedron. It's a 20-sided 3D shape, kind of like a massive multi-sided die you'd use in Dungeons and Dragons.
Okay, I can picture that.
And then they cover that shape entirely in regular hexagons.
So it's basically a giant digital honeycomb wrapping around the entire planet.
Exactly. And the beauty of the honeycomb lies in what mathematicians call the hexagonal invariant.
Which means what exactly?
Well, if you look at a hexagon, it has exactly 6 neighbors. And the distance from the center of our central hexagon to the center of every single one of those 6 neighbors is exactly the same.
Ah, because there are no corners to cut across.
Right.
There are no diagonals like on the chessboard.
None. There is no square root of 2. The distance to neighbor 1 is exactly the same as the distance to neighbor 2, 3, 4, 5, and 6.
They're all equal.
Yes. They all equal a multiple of exactly 1.0. And this allows the computer to perform what the architecture calls uniform step iterations.
Uniform step iteration, so it's just stepping outward evenly.
Right. Expanding a search ring outward to find a driver is no longer a complex trigonometric nightmare. It's just simple, symmetrical addition. You are just adding identical units of distance.
That makes a lot of sense. So the hexagon fixes the heavy math.
It does.
But reading further into the source, they make a point that getting the shape right is really only half the battle. They say that even with a perfect map, traditional spatial databases still completely fail at this scale.
Oh, absolutely.
They talk about something called an R-tree and how it causes a high-right bottleneck. Walk me through this. What is an R-tree?
So to understand the bottleneck, we really have to look at how traditional spatial databases like PostGIS or Elasticsearch actually store geographic locations.
Okay.
They don't just dump coordinates into a giant list. They use R-trees, which stands for rectangle trees.
Rectangle trees.
Yeah, the database groups nearby coordinate points into nested bounding boxes.
Nested bounding boxes, like Russian nesting dolls.
That's a perfect way to visualize it. Imagine Russian nesting dolls, but instead of dolls, they are invisible rectangular boxes covering a map of a city.
Okay, so if I'm in a car, my GPS point is inside a small box that maybe covers just my physical street block.
Right.
And that small box is inside a slightly bigger box that covers my whole neighborhood.
Yes, and that neighborhood box is inside a massive box covering the whole city. Precisely. Now imagine a million cars moving simultaneously.
Oh, boy.
Right. Every time a car moves, which in this system is every 4 seconds, the database has to update.
So it has to constantly open up those Russian nesting dolls.
Exactly. It has to delete the car's old coordinate from one small box, insert the new coordinate into another small box, and then recalculate the size and boundaries of all the larger boxes all the way up to the root of the tree.
Just to ensure everything still fits perfectly. That sounds computationally exhausting.
It's incredibly heavy.
I mean, it's not just updating a location, it's resizing the entire map infrastructure every 4 seconds.
It is brutal. But here is where the real failure actually happens.
Okay.
To make sure the database doesn't get corrupted while it is actively resizing all these nested boxes, it has to use an operating system mechanism called an exclusive mutex lock.
An exclusive lock, meaning it freezes that piece of data so no one else can touch it while it's updating.
Yes. Think of it like a public restroom with only one key.
Okay, I like that analogy.
Only one process can go in, make the updates, and unlock the door when it's done.
Makes sense. You don't want two people messing with the same box at the same time.
Right. So the database locks that specific branch of the tree, makes the updates to the bounding boxes, and unlocks it.
Seems fine for a small system.
But under high load like our Times Square scenario, where you have thousands of cars crossing bounding boxes in the exact same millisecond, you have thousands of ingestion threads trying to grab the exact same lock at the exact same time.
So they just queue up outside the bathroom door.
They queue up. And it causes catastrophic exclusive mutex lock contention.
That sounds bad.
It is.
Yeah.
The system just hangs. And while the threads are waiting outside the door, the operating system's network socket buffers start filling up with new incoming GPS pings.
Because the cars are still moving, they're still sending data.
Exactly. Eventually, those buffers just overflow because data is pouring in faster than the database can write it. You start getting multi-second latency spikes.
And for a system that demands sub-100 millisecond responses.
A 2-second database spike is a complete systemic failure.
Wow.
Driver apps get disconnected, riders see error messages, the whole real-time illusion just shatters.
See, this is a massive aha moment for you. So the problem with squares isn't just the math, and the problem with databases isn't just storage. It is the friction of constant updating.
Exactly.
Which brings us back to H3, because H3 doesn't use nesting boxes or trees at all.
Right, at all. H3 is entirely stateless, and that is really the secret weapon here.
Stateless meaning it doesn't have to remember these shifting boxes.
Exactly. The hexagonal grid is mathematically predefined and completely immutable for the entire planet.
It's just fixed.
Right. The hexagons do not resize, they do not shift, they are permanent mathematical concepts. So, converting a raw GPS latitude and longitude into an H3 hexagonal index requires absolutely zero database lookups and zero exclusive locks.
Wait, I'm confused. If it's not looking up the location in a spatial database, how does the system actually know where the car is?
Because it's pure mathematics.
Just math.
Yeah, it uses constant time, O1, bitwise arithmetic, directly in the application's CPU registers. It bypasses memory and databases entirely.
Okay, you're going to have to unpack bitwise arithmetic for me.
Sure. So deep down, a CPU only understands ones and zeros, right? Bits.
Right.
When a raw GPS coordinate comes in, the H3 library runs an equation. It literally shifts the ones and zeros of the coordinate data left and right using hardware-level logic gates.
Like physically inside the processor.
Yes. It's a calculation that a modern CPU can execute in a single clock cycle. We're talking nanoseconds.
Ugh.
It takes that GPS point, runs the math, and instantly spits out a 64-bit integer. That single string of 64 bits uniquely represents the exact hexagon that car is sitting in on the planet.
So it's not looking at a map at all.
Not at all.
It's just solving a math problem that instantly tells it where on the honeycomb the car is located. And because it's just math happening inside the processor, there are no database locks.
Zero logs.
No queues outside the restroom.
Exactly. Zero contention. You could have 10 million cars pinging the system, and the CPUs would just quietly crunch the bitwise math in parallel without ever stepping on each other's toes.
That is just wild to me. Okay, so we've solved the map itself. We have a perfectly optimized mathematical honeycomb that requires no database locks to update.
Right.
But a honeycomb covering the whole Earth is a lot of data. How does the architecture actually organize these hexagons? Because obviously, a hexagon covering the entire state of New York is very different from a hexagon covering a single street in Manhattan.
Oh, definitely. And the architecture handles that using spatial resolutions.
Yeah. Resolutions, like zoom levels.
Exactly. H3 isn't just one single grid. It is a nested hierarchy of grids. If you zoom out, the hexagons get bigger. If you zoom in, they get smaller.
Okay.
H3 has 16 different zoom levels, or resolutions, ranging from 0, which are massive hexagons, roughly the size of a continent, down to 15, which are tiny hexagons less than a meter across.
Looking at the source, Uber's architecture deliberately relies on two very specific levels to make this whole thing work. Resolution 6 and Resolution 8.
Yeah.
Let's break those down. Why those two?
This is entirely about balancing ingestion throughput, which is how fast we can swallow data against matchmaking latency, how fast we can find a ride.
Okay, so let's start with Resolution 6. The architecture defines this as the metropolitan partition.
Right. It's a massive hexagon with about a 3.2-kilometer radius, so it covers roughly 36 square kilometers.
So basically the size of a large city borough or a massive airport complex.
Yes. And Resolution 6 is used strictly for one purpose, ingesting data into Apache Kafka.
And just to clarify, Kafka is the massive distributed event streaming pipeline that acts as the front door for all the incoming GPS updates, right?
Exactly. It's the ingestion pipeline.
Okay, so Resolution 6 is for the Kafka pipeline. Then we have Resolution 8. The architecture calls this the district match pool.
Right. And this hexagon have a much smaller radius of about 460 meters, less than half a kilometer.
And what does this one do?
Resolution 8 is used strictly for storing the active drivers in the Redis spatial cache. Redis is an incredibly fast in-memory database where the actual matchmaking algorithm runs.
Okay, let me make an analogy here to see if I'm tracking this correctly.
Go for it.
Resolution 6 is like routing a piece of mail to a general city zip code.
Yep.
It's a big bucket. You just want to get the mail to the right processing facility quickly. But Resolution 8 is like finding the exact street block to actually deliver the letter.
That is a brilliant way to frame it. The big bucket for routing, the small bucket for execution. But the crucial part of this architecture is why they must remain separate. Let's imagine we got rid of the big Resolution 6 zip code, and we tried to use the smaller Resolution 8 street blocks for everything, including the Kafka data ingestion.
Okay, what happens?
Well, a car driving at a normal city speed of, say, 40 kilometers per hour would physically cross the boundary of a 460-meter hexagon every 40 seconds.
Okay, so the car is driving, and every 40 seconds it enters a new tiny hexagon. Why does Kafka care if the car crosses a boundary?
To understand that, we need to know how Kafka actually works under the hood. Kafka doesn't just dump data into a pile. It organizes it into sequential logs called partitions.
Partitions?
Yeah, think of a partition like the single conveyor belt in a factory. Kafka relies on partition keys to figure out which conveyor belt to put a piece of data on to ensure the data is processed in the exact order it arrived.
Okay, so it needs to stay in chronological order.
Exactly. But if a car is constantly crossing boundaries every 40 seconds, its data is constantly hopping from one Kafka partition to another.
It's jumping between conveyor belts.
Yes. And this is known as partition hopping. And it completely destroys the chronological order of the data stream.
Why?
Because different partitions process at slightly different millisecond speeds depending on server load. So you might accidentally process a driver's location from 10 seconds ago after you've already processed their location from 2 seconds ago.
Oh, so the matchmaking system would look at the map and the car would appear to be driving backward.
Or just teleporting wildly down the street.
It basically creates a time travel glitch in the Matrix.
Exactly. It breaks reality.
Ah.
But by using the massive 3.2-kilometer Resolution 6 hexagon as the Kafka partition key, a driver is encapsulated in a single partition for 10, 20, maybe even 30 minutes at a time.
They stay on one conveyor belt.
Right. This guarantees strict, in-order chronological stream processing while keeping the total number of data partitions highly manageable for the servers.
That makes perfect sense for the incoming fire hose. But on the flip side, why not just use that big Resolution 6 zip code for everything? Why do we need to step down to the smaller Resolution 8 street block for the Redis memory cache?
It all comes down to that 100-millisecond latency constraint we talked about.
The speed?
Right. If Redis stored drivers using the massive Resolution 6 zip code, a single database key representing, say, Midtown Manhattan would hold upwards of 15,000 active drivers at any given moment during rush hour.
15,000 drivers in one bucket. And when my app tries to find me a ride, it has to mathematically scan all 15,000 of them.
Yes. The matchmaker would completely choke trying to filter, sort, and run vector scoring algorithms on 15,000 drivers every time someone hit request.
It would take seconds, not milliseconds.
Exactly. By stepping down to resolution 8, that 460-meter street block, the localized cluster of active drivers drops to a highly manageable pool of maybe 20 to 80 cars.
And scanning 80 cars is fast.
Very fast. Scanning, sorting, and scoring 80 drivers takes less than 2 milliseconds. It is mathematically optimized for pure execution speed.
See, here is where the source material gets deeply fascinating to me. We have these two different zoom levels, the big zip code and the small street block. But the system has to constantly translate between them.
Right.
And the source talks about a feature called hierarchical prefix co-location. The way they describe it, it sounds like absolute magic.
It is arguably one of the most elegant engineering features of the entire H3 system.
How does it work?
Remember how we said every hexagon is identified by a unique 64-bit integer?
A string of 64 ones and zeros, yeah.
Here is the secret. Because of the way the honeycomb is geometrically nested, every smaller child cell, like our resolution 8 street block, strictly resides within the boundary of a coarser parent cell, our resolution 6 zip code.
Right. The street block is physically inside the zip code on the map.
Yes. And because of that physical nesting, H3 is designed so that the child cell inherits and shares the exact same leading binary bits as its parent cell.
Wait, really?
Yes, the prefix of the string of ones and nuis is completely identical.
So if the zip code is, say, 1011, the street block starts with 0011 and just adds some extra numbers at the end.
Exactly. Now think about what that means for computing. To figure out what broader city partition a specific street block belongs to, the computer does not have to look at a map.
It doesn't have to draw a polygon?
It doesn't have to ask a database.
It just chops off the end of the number.
Yes. It executes a microsecond bit shift operation. The CPU simply truncates the end of the resolution 8 binary string, looks at the remaining prefix, and instantly knows its resolution 6 parent.
Zero geometric calculations required.
None. It's just comparing two strings of text.
That is brilliant. It takes a complex geographic relationship and turns it into a basic text matching problem.
It is. But the implications go far beyond just saving a few CPU cycles. It profoundly impacts the physical hardware of the database servers.
How so?
Because all the child cells in a neighborhood share the same numerical prefix, databases naturally sort them sequentially.
Okay.
Which means they store them right next to each other on the physical hard drives.
Wait, on the actual spinning disks or solid-state drives of the server? Like physical proximity on the hardware?
Yes, on the silicon itself. Geographically adjacent child updates are grouped on contiguous disk pages. This maximizes sequential read throughput.
So it's physically grouped.
Right. When the database needs to pull data for a whole neighborhood, the hard drive's read mechanism doesn't have to bounce all over the disk, randomly searching for neighboring streets.
Because that bouncing takes time.
Exactly. The data for those streets is literally physically touching on the server's silicon.
That is mind-blowing. They are taking real-world physical geography, like the actual streets of New York, and mirroring it flawlessly onto the microscopic physical geography of a server rack.
It's beautiful engineering.
Okay, so we understand the map. We understand how the data is sorted into zip codes and street blocks. But let's go back to our Times Square scenario.
It's still raining.
It's still raining. Let's say there are 5,000 cars in that immediate area, all pinging their location in the exact same second. How does the system physically swallow that much data without the web servers just crashing?
To handle this kind of load, you really have to throw away the traditional rules of web architecture.
Okay.
The source details a 5-level ingestion pipeline. Let's walk through the physical journey of a single location update.
Right. Level 1 is the emission from the phone itself, right?
Correct. The driver's smartphone captures raw GPS sensor readings, latitude, longitude, their speed, the bearing they are traveling. It does this every 4 seconds.
Okay.
But it doesn't send this as a bulky text file. It serializes this data into a highly compressed binary format called protobuf, or protocol buffers.
Why protobuf?
Protobuf is about 80% smaller and much faster to parse than standard JSON text, which is what most web apps use.
So it's shrinking the payload before it even leaves the phone?
Yes. It sends this tightly packed binary data over a persistent gRPC HTTP2 stream. The data flows across the cellular network and hits the edge of Uber's infrastructure, which is a gateway called Envoy.
Okay, so Envoy is the bouncer at the club.
Exactly. Envoy terminates the connection, applies rate limiting so a hacked phone can't spam the system with fake pings, and passes the payload to the ingestion workers.
And this is where things get tricky, right?
Yes. Here's where standard web architecture hits a massive wall. The source material explicitly notes that traditional, popular web frameworks like Java or Spring Boot were completely rejected for this core ingestion system.
No, I found that really surprising because Java practically runs half the internet. Why reject it here?
It comes down to how standard web servers manage memory. Usually when a web server receives an incoming request, say you clicking a link on a website, it dynamically allocates a tiny block of memory on the server.
Right, it makes space for it.
Yeah, it creates a temporary object to hold that request data while it processes it. When the server is done sending you the web page, it just throws that temporary memory object away.
Okay, so it's like an office worker making a new digital folder for every piece of paper that comes across their desk, writing some notes on it, and then shredding it a millisecond later when they're done.
That's a perfect analogy.
Yeah.
Now, at 5,000 requests a second, creating and shredding folders is fine. The server can easily keep up.
Okay.
But remember, our peak traffic, 250,000 to 500,000 requests per second.
Oh, right.
Creating and destroying 500,000 temporary memory folders every single second triggers a massive crisis in the server's memory management system. Specifically, a mechanism called garbage collection.
I've heard of garbage collection. It's basically the automated janitor program running inside Java that goes around cleaning up all those shredded digital folders so the server doesn't run out of RAM, right?
Exactly. But when you have 500,000 new folders being shredded every second, the janitor gets completely overwhelmed.
I can't sweep fast enough.
No. And to do its job without corrupting the active data, the garbage collector has to periodically halt the entire application to clean up the memory heap. This is known in computer science as a stop-the-world pause.
Wait, the server literally stops thinking.
It completely freezes. It pauses all execution. For maybe 100 or 200 milliseconds, the server does absolutely nothing but clean memory.
That sounds dangerous.
It is, because here is the cascade failure. During that 200 millisecond pause, the network socket buffers in the operating system are still receiving new incoming GPS pings from the cellular network.
Because the cars don't know the server paused.
Right. The data is piling up at the door, but the server isn't answering.
So the buffers overflow.
The buffers overflow, and the operating system starts dropping driver connections. Hundreds of thousands of driver apps suddenly lose their sync with the server.
And what do the apps do when they lose connection?
They automatically retry.
Mm-hmm.
Now you have a retry storm on top of the original traffic, and the entire system crashes.
Wow. So if you can't use dynamic memory allocation, and you can't make new digital folders because it summons the garbage collector, how do you process the data?
You introduce an absolute marvel of low-latency engineering called a lock-free ring buffer, heavily inspired by the LMAX disruptor pattern.
The LMAX disruptor.
Yeah, and you build it in highly performant, low-level languages like Go or Rust.
Okay, I really need you to unpack the ring buffer for me. Instead of making a new folder for every piece of data, are they just reusing the exact same empty folders over and over in a giant circle?
That is precisely what they are doing. A ring buffer is a pre-allocated fixed-size circular array sitting directly in native memory.
Pre-allocated.
Yeah, when the ingestion server boots up, before any data even arrives, it creates a circle of, say, 10,000 empty memory slots.
And it never makes a new slot ever again.
Never. The memory is fixed. When a binary GPS ping arrives from Envoy, an ingestion thread needs to claim an empty slot. But it doesn't use those slow mutex locks we talked about earlier.
The bathroom door lock.
Right. It avoids that completely. It uses a hardware-level CPU instruction called a compare and swap pointer increment.
Compare and swap. How does that avoid a bottleneck if multiple threads are trying to grab a slot at the same exact time?
Think of it like a highly efficient hotel clerk.
Okay.
If two guests walk up at the exact same time wanting a room, the clerk doesn't ask them to wait in line while he goes to check the physical rooms. The clerk looks at his ledger, compares the current available room number, assigns it to guest A, and swaps the ledger to the next number, all in one single, uninterrupted motion.
It's immediate.
It's an atomic operation. Guest B instantly gets the next room. There's absolutely no waiting.
Okay, so the system atomically claims slot 1, writes the GPS data, and moves on. The next ping goes to slot 2, then 3, all the way around the ring.
And here's the magic. When the pointer hits slot 10,000, it just loops back around to slot 1.
But wait, what about the data that was already in slot 1?
By the time it gets there, the data that was originally in slot 1 has long since been processed and sent to Kafka. So the system just quietly overwrites the old data with the new data.
That completely eliminates the garbage collector.
It does.
There is no memory janitor needed because nothing is ever thrown away. It is simply overwritten in a continuous circle.
Exactly. Zero dynamic allocation overhead. Zero stop-the-world pauses.
That's genius.
But the engineers went even further. To maximize throughput, They utilize an operating system technique called zero-copy byte transfer.
What does that mean? How do you transfer data without copying it?
Well, normally when data arrives at a server's network card, the operating system kernel copies that data into its own memory.
Okay.
Then it copies it again into the application's memory space, the user space, so the actual software can read it.
That sounds incredibly inefficient. You're moving the exact same data twice just to look at it.
It is highly inefficient. With zero copy, the application commands the hardware to use DMA, direct memory access.
Direct memory access.
Yes. It instructs the network socket to move the raw location bytes directly into the Kafka producer socket buffer. The data never actually enters the user space application memory.
It just bypasses it.
It's a direct hardware-level bypass. This technique alone slashes CPU usage by over 70%.
That is staggering. It's like routing a rushing river directly into a municipal pipeline without ever letting the water touch the ground. It just flows right through the hardware.
That's exactly what's happening.
But the source material mentions a risk here. If this ingestion pipeline is so insanely fast, taking in 500,000 pings a second, what happens if there's a massive, unprecedented anomaly?
Like a massive spike in traffic.
Yeah, say a huge concert ends and suddenly 2 million drivers ping at once. Could it overwhelm the system and prevent the riders from booking cars?
This brings up a critical concept in distributed systems called fault domain isolation, or blast radius reduction.
Blast radius reduction, I like that term.
The engineers foresaw that exact risk. So they implemented a dual buffer isolation pattern. They physically separate the memory ring buffer used for driver location updates from a completely different memory ring buffer used exclusively for rider match requests.
Oh, I see. So it's not one giant highway. It's two entirely separate, physically isolated highways.
Precisely. It acts as a strict circuit breaker. Even if a massive anomaly saturates the driver ingestion buffer, causing drivers to experience a slight delay in their map updating, it will never delay or crash the rider buffer.
Because they don't touch.
Exactly. You, standing in Times Square trying to book a car, will still get your request processed in sub 100 milliseconds because your highway is completely clear. The chaos of the drivers cannot physically touch the rider requests in memory.
Okay, let's just take a breath here because the speed of this entire pipeline is incredible. The system has successfully ingested the data from 1 million phones. It bypassed the Java memory janitor using ring buffers.
Right.
It used bitwise math to pinpoint everyone's exact hexagonal street block without using database locks. And it updated the Redis spatial cache.
Yes.
And it did all of this in under 2 milliseconds.
It's astonishing.
Now let's return to you, the listener, standing in the rain in Times Square. You hit request. The system now knows exactly where you are and exactly where all the cars are. How does the architecture actually pick your specific driver?
When you hit request, the system triggers the proximity matchmaker worker. This worker faces a classic data problem known as a combinatorial search space.
Which means it has too many options.
Right. It obviously cannot mathematically scan all 1 million global drivers to find you a ride. It has to scan locally.
Right. It looks inside our Resolution 8 street block, the district match pool that we stored in the Redis memory cache.
Yes. The system maps your exact Times Square GPS coordinates to a specific Resolution 8 central hexagon. In the architecture, this central hexagon is denoted as k = 0.
A0.
But immediately we run into a major edge case problem called the boundary hazard.
The border problem. Tell me how this breaks the matchmaking.
Well, imagine a scenario where you are standing right on the physical edge of your K0 hexagon boundary. There might be a driver sitting in traffic just 50 meters away from you, the absolute perfect match. But they are physically located just across the invisible boundary line, sitting in the neighboring hexagon.
So if the system only queries my KOE hexagon, it won't even see that driver.
It's completely blind to them.
It might match me with someone 400 meters away on the complete opposite side of my own hexagon just because they are technically in the same bucket. That is a terrible user experience.
A naive spatial database would do exactly that. It would return the suboptimal driver.
So how do they fix it?
To solve the boundary hazard, the H3 architecture utilizes a technique called concentric K-ring expansion.
Concentric expansion.
Because every hexagon has exactly 6 equidistant neighbors, the mathematical expansion is incredibly fast. The system doesn't just query your KO or center cell, it instantly expands the search to K1.
What does the K1 ring include?
K1 includes your center cell plus the inner ring of the 6 adjacent hexagons surrounding it.
So it's spreading out.
Yes. This instantly expands the search area to 7 total cells, covering a radius of about 1.2 kilometers.
And if there still aren't enough cars in those 7 cells?
It seamlessly extends to K2, the outer ring. This adds 12 more adjacent hexagons, bringing the total to 19 cells and creating a 2.5-kilometer search radius.
And because H3 is an equidistant grid?
This expansion takes constant O1 time. It requires no complex geometric joins in a database. The system simply pulls the driver IDs from those 19 specific Redis keys using a highly optimized, pipelined, multi-key read.
Explain the pipelined part of that. Why not just ask for them one by one?
Because latency. Instead of asking Redis for cell 1, waiting for the answer, then asking for cell 2, the pipeline sends all 19 requests to Redis in a single network packet.
Oh, wow.
Redis processes them in bulk and returns all the active drivers in that 2.5-kilometer bubble in a single response.
So it grabs a massive pool of potential drivers instantly.
It does.
But the source material makes a fascinating point right here, which challenges a basic assumption I always had about ride-sharing.
What's that?
I always assumed the app just gave you the closest car, but the document says the closest driver is rarely the best driver.
Oh, absolutely not.
It's like picking a checkout line at the grocery store. The shortest line might have a broken register or a customer with 100 coupons. You don't just want the closest line, you want the fastest line. What else is the system looking at besides just raw physical distance?
This is where the sheer computational power of the system shines through multi-factor vector scoring.
Vector scoring.
Yes, the system doesn't just rank the drivers by distance. It runs an algorithm that weighs multiple real-time behavioral variables to predict the most successful overall trip outcome.
So it's predicting success.
Distance, specifically the estimated time of arrival, or ETA, is obviously the primary weight. It is denoted in the algorithm as W1, and it accounts for roughly 50% of the total score.
Okay, so ETA is half the battle. What makes up the other 50%?
The algorithm evaluates the human element. First, it looks at the driver rating, which is W2, weighted at 20%.
That makes sense. The system actively wants to pair you with a highly rated driver to ensure a good experience.
Exactly. But then it looks at historical behavioral metrics. W3 is the driver cancellation rate, weighted at 15%.
Why is cancellation rate so heavily weighted?
Because a driver who accepts a ride and then cancels 3 minutes later completely destroys marketplace liquidity.
It's incredibly frustrating for riders.
It is, and it forces the system to start the entire process over.
Yeah.
The algorithm actively penalizes uncommitted drivers who have a high history of canceling.
Oh, wow. So if driver A is physically closer to me, but they have a history of canceling rides, they might actually lose the match to driver B, who is a minute further away but has a flawless completion record.
Absolutely. The algorithm optimizes for completion, not just proximity. And finally, W4 is the acceptance rate, also at 15%.
So rewarding drivers who accept quickly.
Right. This rewards drivers who consistently accept the rides offered to them, which minimizes the time the back-end system spends hunting for a willing driver.
So the algorithm pulls this pool of 80 drivers from the hexagonal rings. It scores every single one of them on ETA, their 5-star rating, their cancellation history, and their acceptance rate.
Yes.
It sorts them into a perfectly ranked list of candidates. And because all this driver data is sitting in that lightning-fast Redis memory cache, this entire process from tapping the button to generating the ranked list of the best human beings for the job happens in under 2.0 milliseconds.
It is a triumph of localized in-memory computing.
Yeah.
But as we just alluded to with the scoring metrics, the math is perfect, but the real world is incredibly messy.
Humans are messy. We are unpredictable.
Very messy. The bitwise math has chosen the absolute perfect optimized driver for you in Times Square.
Okay.
But what if that driver is currently navigating a tight turn, ignores their phone, and misses the ping? Or what if they see it's Times Square, decide they don't want to deal with the traffic, and hit decline?
Right. How does a mathematically perfect architecture handle human unpredictability?
This brings us to the final and arguably most crucial mechanism in the system. The source calls it the sequential batch offering protocol.
Sequential batch offering. Break that down.
Once the vector scoring algorithm has identified the top-ranked driver, the system has to offer them the trip. But it doesn't just broadcast the offer to the top 5 drivers at once, hoping someone takes it.
It doesn't want them fighting over it.
Right. It executes a sequential protocol. It asks the absolute best driver first.
But while it's asking that driver, it has to make sure no one else in the system steals them. Right? Like double booking a seat on an airplane. You can't have 2 people trying to check out with the same driver.
Precisely. To prevent double booking, the system executes an atomic Lewis script directly inside the Redis cluster.
An atomic Lewis script.
Yeah. The script is called reservedriver.loop. This script places a rigid, unbreakable 10-second fencing lock on that specific driver's record in the database. Their state changes to reserved.
So if another rider at a hotel just down the street requests a trip in that exact same millisecond, and their local carrying overlaps with mine,
The system will look at that locked driver and say, nope, they are taken.
it will completely bypass them in the search space.
Exactly. So the chosen driver's phone buzzes, they see the route, they see the estimated fare, and they see a 10-second countdown timer.
If the driver taps accept, great, the trip moves forward. But if they ignore it, or if they actively tap decline, how does the system recover? Does it have to rerun the entire hexagonal search and do all the vector math again?
No, because that would be a massive waste of computational power and time. The architecture is designed for immediate self-healing.
How so?
The moment that 10-second timer expires, or the moment the driver hits decline, the Redis fencing lock instantly releases. That driver is thrown back into the available pool for other people. But for your request, the system simply moves down the ranked list it already calculated.
It just goes to candidate number 2.
Exactly. It sends candidate number 2 the offer with a fresh 10-second lock. It cascades down the list until someone accepts.
That is incredibly efficient. But I have to ask the edge case question here.
Go for it.
What if the list is empty? What if it's 3:00 a.m. in a quiet suburb and rings K0, K1, and K2 have absolutely zero available drivers? Does the app just throw an error and say no rides available?
The system tries extremely hard to never show that message. If the local rings are completely empty, the matchmaker triggers an asynchronous radius expansion.
It goes wider.
It jumps out to K3. That encompasses 37 hexagonal cells covering a 4.5-kilometer radius.
So it casts a much wider net, looking for anyone willing to drive a bit further to get you.
Yes, but here is the most fascinating part. While it's searching that wider net, the system simultaneously spins up an Apache Flink streaming engine.
Flink.
Flink is designed for real-time analytics. It looks at the ratio of riders requesting cars versus the severe lack of available drivers in that specific H3 cell. It calculates this supply and demand imbalance across 5-second tumbling windows.
Oh, I see where this is going.
And based on that imbalance, it instantly calculates a surge pricing multiplier.
Ah, surge pricing. I always thought of surge pricing as just a purely financial mechanism to make more money during busy times. But you're saying it's actually an architectural mechanism to physically move supply.
It is real-world physical orchestration via distributed streaming analytics. By flashing a surge heat map on the driver's screens, it financially incentivizes drivers who are sitting idle in neighboring areas to turn their steering wheels and physically drive their cars toward the empty zone.
The system uses price to heal the spatial imbalance.
Exactly.
That is a brilliant way to merge economics and software architecture. Okay, so all of this complex state management, the 10-second locks, the cascade down the list, the surge calculations, this is all happening in Redis.
Right.
But Redis is an in-memory cache. It's incredibly fast, but it's ephemeral. If a server rack loses power or a process crashes, everything in that RAM is instantly wiped out. How does the system keep a permanent, unshakable record of who actually took the ride and who owes what money?
That is exactly why Redis is only half of the matchmaking core. While Redis handles the ephemeral, millisecond by millisecond chaos of the matchmaking dance, the architecture relies on a completely different database called ScyllaDB to act as the master ledger.
ScyllaDB. The source calls this the trip lifecycle state machine.
Yes, ScyllaDB is a deeply persistent, heavy-duty, disk-based database. When you request a ride, ScyllaDB creates a permanent record in an active trips table. It sets the state of your trip to requested.
Okay.
When the Redis lock is placed on a driver, ScyllaDB updates the state to offered. When the driver taps yes, it becomes accepted. When they physically pick you up, it moves to in progress, and finally when you get out of the car, completed.
But wait, in a distributed system spanning multiple data centers, network lag is a reality. What if a network hiccup causes an accepted message to arrive at ScyllaDB before the offered message arrives? Doesn't that corrupt the entire state machine?
That is a classic distributed systems dilemma. If the database processed them out of order, it would cause massive bugs. To solve this, ScyllaDB employs OCC, or Optimistic Concurrency Control.
How does OCC prevent the out-of-order messages?
Every state change requires a strict version number increment. Requested is version 1, offered is version 2, accepted is version 3.
Just a simple count.
If a delayed message arrives trying to update the trip to version 2 offered, when the database has already progressed to version 3, expected ScyllaDB looks at the version numbers and explicitly rejects the stale update.
It says, I am already past this.
Exactly. The state machine can strictly only move forward.
So Redis is the brain that handles the speed, and ScyllaDB is the memory that handles the ultimate truth.
Perfectly summarized. And through a native change data capture engine, a CDC, every single time ScyllaDB updates that state, it streams that undeniable fact out to downstream microservices.
Like what?
It triggers the payment gateway that will eventually charge your credit card, it updates the safety tracking systems, and it pings the notification service that actually buzzes your phone.
Which brings us all the way back to you, the listener, standing in Times Square.
Still in the rain.
The rain is falling. You tap Request. In the first millisecond, Envoy gateways and lock-free ring buffers route your tiny digital request past the chaos of 500,000 global GPS pings, bypassing the garbage collector entirely.
Right.
In the second millisecond, the CPU uses raw bitwise math to pinpoint your exact H3 hexagonal street block without a single database lock. In the third millisecond, Redis expands concentric K-rings outward, finds 80 nearby cars, runs a multi-factor vector scoring algorithm on ETA and driver behavior, and slaps an atomic fencing lock on the absolute best match.
The driver accepts.
ScyllaDB increments the master ledger to accept it, and a WebSocket fires a signal back across the cellular network.
And your phone buzzes.
Your phone buzzes, and that little digital car icon starts moving toward you on the map. You are witnessing the culmination of lock-free memory rings, bitwise hexagonal mathematics, zero copy byte transfers, and optimistic concurrency control, all executed flawlessly in the literal blink of an eye.
When you really understand the engineering beneath it, it completely reframes what an app actually is. You aren't just opening a map. You are peering through a window into a massive, globally synchronized sub-millisecond supercomputer that is continuously solving a planetary-scale puzzle.
It really does change how you will view your next ride. Every time you see that car icon turn a corner on your screen, you'll know there's a 64-bit integer shifting in a server rack somewhere, making it happen.
It's beautiful.
So we'll leave you with a final provocative thought to chew on. If we can mathematically tessellate the globe into perfectly equidistant hexagons to efficiently route 1 million chaotic human drivers with sub-2 millisecond latency, what other massive broken systems in our world are just waiting for a hexagonal revolution?
I mean, the possibilities are endless.
Could we use this exact same stateless, lock-free architecture to optimize global supply chains and port logistics? Could we track complex energy grids in real time to prevent blackouts? Or even orchestrate massive fleets of autonomous emergency drones during natural disasters?
It's definitely coming.
Next time you look at a digital map, ask yourself, why are we still limiting ourselves to thinking in squares?